Hello students, we are coming into about 1/3 of our course that we were to study in contemporary world architecture or modern world architecture this time. And that also you need to understand a very small thing that the word modern world architecture or the term modern world architecture is not synonymous with contemporary world architecture. Modern world architecture refers to the architecture of the modern times, predominantly the architecture of the 20th century that brought about a very tremendous revolution in an architectural thinking. Contemporary, on the other hand, refers to the architecture that is in our world today. In this subject that we have taken up to teach you, we will be covering the contemporary aspects of modern architecture also, that the later years stepping into the 21st century and what all changes took place, what all new concepts came. So, that continuity of modern architecture going on into contemporary world architecture would be the ending of this particular course. And hopefully we will be able to talk about a lot of interesting buildings even as we end this course in the 21st century. Now we have been talking about skyscrapers. I have talked to you about various kinds of skyscrapers. We have shared several examples of some very interesting and innovative skyscrapers globally. Some we have only mentioned them, some we have talked about in detail, like the bioclimatic skyscraper, the Commerce Bank, we talked about the Swiss Re, we talked about the Hertz Tower, and the very fact that it is a low carbon building because it uses material that can be recycled up to 85%, and the steel that is already used is of recyclable, is recycled itself. So tremendous amount of work being done in the world of sustainability and low carbon construction, etc. And all these theories are getting or are getting imbibed into our buildings in the 21st century particularly. But like I said yesterday also, that we keep on going back and forth from old to new buildings, so that I continue to knit this tapestry of modern world architecture for you. And maybe at certain points you might feel disconnected, but when in the end you will see the complete picture, you will realize this is where we were headed. Right now I would say keep on getting all that information, all these lectures, keep on putting the buildings in their rightful place, and you will see the picture emerging. The reason why I keep on going back and forth is because what idea I talk about today has an impact on the building of tomorrow or the building in the 21st century. If I was not to show you that impact and wait for it to come in a series or a chain of slide presentations, I would miss the opportunity of getting it connected to the idea when and where I am talking about it. So that is why I prefer that if I am talking about it now, let me connect it to that building now itself so that you see the link. And also by going back and forth, a kind of lukewarmness that might start coming, that we are focusing on only certain kind of older kind of buildings which we are not very keen on, that kind of disappears because we keep on going forth to certain latest buildings in the course of our discussion. So now I will take you a little back. I will take you into the 1950s, and I will take you at a time when skyscraper construction really took off in steel and glass. You know, based on our discussions, that skyscrapers had started evolving out of the Chicago school, and lot of advancements were made at the time, whether it was the vertical transportation system by Otis, the elevator, whether it was the right foundation for the muddy soil of Chicago, whether it was fireproofing of the steel structural frame, whether it was the use of steel as the structural frame, the use of glass as somewhat like a curtain walling, all these ideas came in Chicago school and gave that deep push needed for the skyscrapers to become the modern world's one dominant built form all over the world. But when we come to the standard glass and steel skyscraper of the 20th century, this was the structural system which was the backbone of the skyscraper, and its critical role was to provide safety, efficiency and overall design. The important structural considerations used to be, one is it should have the capacity to bear load. Now load, not only the vertical or the gravity load that falls on all buildings or all forms, but also because skyscrapers had the added disadvantage of having lateral load in the horizontal direction coming from winds and even earthquake or seismic loading. So if it is a building which is small, short in height, this is not much of a problem, but for taller buildings or skyscrapers, this was a problem which was a bigger loading problem than the vertical or the gravity loading. Therefore, in skyscrapers, the controlling factor in design used to be the lateral load. Now, the second thing we look at when we design skyscrapers is wind and seismic resistance. All skyscrapers are subjected to strong winds and also to seismic activity. That depends on which region of the world the building is coming up in. Structural innovations that help us in mitigating this impact, particularly of seismic activity, are tuned mass dampers. We talked about that in the building type A 101 and I had explained it to you. We talk about outrigger systems like we see here in this building. This kind of an outrigger system is created, or die-grid structures. We talked about it when we talked about the Swiss Re building and the Hearst Tower, that they are designed using the die-grid structure, and these kind of structural systems reduce sway and prevent structural failure. Now third is material efficiency and sustainability. We use high strength steel today, we use RCC and we use composite materials to optimize the strength of the material, whereas minimizing the weight. Thus we reduce cost and the environmental impact. We optimize strength while reducing the weight of the product. We try to reduce both cost and we try to reduce the environmental impact. When it comes to maximizing usable space, we try to go in for skeletal frameworks that allow for open floor plans and thus increase the net usable indoor space. Third is the speed of construction. There are a lot of structural advancements today that help us to build skyscrapers very fast. They can be done through prefabrication and modular coordination or model construction that already come, and something like the slip form concrete cores, which I will show you, that enable skyscrapers to be built faster and more efficiently. We already know in Chicago, because of the standard size of steel beams and steel columns that have to be riveted, bolted or welded on site, they had realized that the steel frame of the building could be erected very fast in a matter of weeks. Now when we are talking of skyscrapers many times taller than those Chicago school buildings, we require much faster techniques to build them. And this is one of those methods which was also used in the tallest building in the world, the Burj Khalifa, the slip form concrete core construction. And here there is a continuous moving framework that you see the picture of the moving framework. It is a continuous moving framework for making the elevator shafts and stairwells and shear walls which form the structural spine of the skyscraper. Concrete is poured continuously into the formwork system, which keeps moving upwards continually at about 15 to 30 centimeters per hour and never stops in middle. When the construction is going on, it runs 24/7 till that particular core is completed. The formwork is raised as the concrete sets and reinforcement bars are added progressively during the process of construction. So here you see this picture shows us how with time the platform has been raised up, the slip form concrete core has been raised up and the building's height has gone up somewhat, and thus so doing, running it 24/7, we are able to complete the main spine, structural spine of the building. Now the sixth thing that we look at, just to revise the things that we have seen, we look at the load bearing capacity. We are worried about the wind and seismic resistance. We are concerned about material efficiency and sustainability. We are concerned about maximizing the indoor usable space. We are concerned about the speed at which we are constructing these buildings. And then there is architectural flexibility. Strong, lightweight structural systems We have daring architectural forms from twisted skyscrapers like the Shanghai Tower to the very ultra slender 111 West 57th Street building in New York in 2022. So these are the various novelties or various ways in which the buildings are coming up today, and they have tremendous architectural flexibility. Then is fire safety and redundancy. With regard to fire safety, we have fire resistant materials and they prevent progressive collapse prevention to enhance the safety of the building. RCC cores are used along with multiple load paths, thus providing redundancy in case of failure. What does it mean? It means that there is enough structural backup given in case the regular structural members fail. There are these so called redundant structural backups that will take up the load of the building and prevent it from collapsing or falling or getting completely ruined. And these redundant members are always provided in skyscrapers, though they may not be active on a day-to-day basis, but they come into play as soon as the main structural members carrying the load, whether the vertical or the lateral load, when they fail, they start or they come into play. Now, in way back in the 20th century, the one person who was responsible for the design of the modern day skyscraper, the structural design, was the engineer, Bangladeshi engineer Fazlur Khan, and he used to work with Skidmore, Owings and Merrill. He was really a master engineer regarding the design, or he is said to be the engineer behind the design of the modern skyscraper. He had given this graph that actually shows you the lower curve is a theoretical design of gravity loads exclusively, and it shows that if your building height is approximately 100 stories, then you would require around 25 pounds per square feet of steel. But when it comes to lateral loading, the curve is the upper curve that clearly shows the amount of steel required for lateral resistance, and that is about 65 pounds per square feet for a building about 100 stories high. This figure shows you the evolution of various structural systems that has taken place over particularly the 20th century, late 20th century and into the 21st century. You find that we began with a simple moment frame initially, and then we went on to add shear truss, we went on to add tube in tube, we worked with bundle tube. Lot of variations are available or were made available in the design of the skyscrapers. Now, if we look at the simple steel moment frame system that was used by Mies van der Rohe in his classic Seagram building, very generic and simple moment resisting frame MRF, in which the beams and columns are rigidly connected to resist both vertical, that is gravity, as well as horizontal load, that is lateral load of winds, etc., and do not need to rely on shear walls or bracing. The connections between the beams and the columns is more than enough to take care of both kinds of loading. The steel was fireproof by encasing it in concrete. It was standard practice because modern waterproof coatings were fireproof coatings had not yet been introduced, and the perimeter and core columns, the distribution of loads was done through exterior columns and the inner service core with elevators, stairs and mechanical systems in the internal service core or the inner service core. What was the architectural influence of the moment frame? It was very massive at the time because lot of such cuboidal glass and steel buildings came up all over the world. It had an open floor plan with minimum internal columns. It had a glass curtain wall, as you see here in the Liver House by Skidmore, Owings and Merrill, across the road from the Seagram Building, and it was the hallmark of Mies van der Rohe's international style. Most of the skyscrapers of the time were influenced by this in the 1960s. But then the limitation of the moment frame system became obvious, that if you wanted to build taller, than the Seagram or the lever house, etc., we realized that the moment frame was less efficient when it came to lateral loading, that is wind forces, etc. And therefore, taller skyscrapers like the John Hancock Center or the Willis Tower, they required something called a tube system, where there is minimum material use but there is increased stiffness. In the tube system, the building is designed to act like a hollow cantilevered cylinder to resist lateral loads. It is a cylinder, it is cantilevered in the vertical direction. It is cantilevered in the ground, it is cantilevered from the ground all the way up, and this cylinder, it works and resists lateral loads. Now, innovative lateral stability systems for designing taller and more efficient buildings was this method. The pioneer again was civil engineer Fazlur Khan of Skidmore, Owings and Merrill, and he designed the 43-story high Dwight Chestnut apartment building in Chicago in 1966 to highlight the principle of the tube system. It was constructed using steel, concrete, and it was a composite construction. Now, various type of tube structures then evolved. There is the simple one, the frame tube, the Barris tube, the tube in tube, bundle tube, and then hybrid tube. We will look at them one by one. The frame tube. Essentially, frame tube is a perforated tube, as you see here, which is cantilevered or it's standing on the ground. This kind of cylinder perforated and standing vertically on the ground or cantilevered from the ground. When subjected to lateral or wind forces, it behaves partially like a tube, that is, it increases bending stiffness, it is not easily able to bend, and partially it acts like a rigid frame, thus helping us with gravity loads. So, this one tube serves two functions, both taking care of the lateral load as well as the vertical load or the gravity load. Now, if we take that example of the Dwight Chestnut building, for example, here we have the exterior perimeter frame, closely spaced columns which are tied with the deep spandrel beams, right. So, what is the spandrel? If there is a window above and a window below and there are windows on the side, then this area in between them is called the spandrel. And in this kind of structure, you would find that these here all across, they become spandrel beams in between the two floors of windows. So you have a complete grid that is formed, like this, very closely spaced of beams and columns, spandrel beams and columns closely spaced. The disadvantage being very small window openings, and they are able to resist lateral loads of wind and seismic load, etc., just as a tube would. And the distance from the tube, the outer tube which you see here, and the inner core is spanned with beams and trusses. So, the outer tube and the inner core are connected with each other through beams and trusses. What is the advantage of that? This maximizes the effectiveness of the perimeter tube, the outer tube, because some of the gravity load from the core gets transferred to the outer tube. Because of these trusses and beams connecting the core and tube, some of the gravity load from the core gets transferred to the tube, and thus the tube is able to carry some gravity load. The other advantage is, because of the gravity load and because of it being pushed down, the tube becomes more stable and prevents from being overturned due to the lateral load. It is very interesting. You see, when the gravity load is transferred from the core to the outer tube, and gravity is now pulling the tube downwards, it is thus helping the tube that when wind forces strike it, for which it has been designed to bear it, it will give him that additional benefit of not easily overturning because the gravity load is pulling it down. I hope you understand it. So, it is most widely used, the frame tube, and it was used by Aeon Center in the US by Edward Durrell Stone in 1973. He is the same architect who designed the US Embassy in Delhi, and in variety of floor plan shapes including squares, rectangular, circular, free form, the frame tube mechanism has been used. Again you see, if you see the plan of the Aeon Center here, the interior columns are few and at core, interior columns few and at core in this part, and then the whole core, the building interior is completely free of columns, and on the outer side you have the tube, the perimeter tube, which has the closely spaced columns and spandrel beams. Now this was also true in the World Trade Center towers. This is the plan of the World Trade Center tower, where again you find these closely spaced columns and spandrel beams, a very dense mesh forming the tube on the outer periphery. Then you have the inner core and all the columns, inner columns concentrated here. There are no columns in this area, which is completely column free, but there are beams and trusses that are linking the core to the outer tube so as to provide some load transfer of gravity load towards the outer column, as I mentioned earlier. The distance between the tube, this tube, and this core are spanned with beams, and this entire area is left completely column free, which maximizes the effectiveness of the tube by transferring some gravity load to the tube, and again reminding you, it increases its ability to resist overturning due to wind forces or lateral load. Interior columns are few and at the core, and therefore it is mostly column free interiors on the inside. When we look at the John Hancock Center now, which was 100 stories high, 344 meters tall, done by Skidmore, Owings and Merrill, with chief designer being Bruce Graham, structural engineer Fazlur Khan, executed in 1968, was the 4th tallest in Chicago, 7th tallest in the United States. It had offices and restaurants, it had 700 condominiums, and was 3rd highest residence in the world, and lot of other features were there in this building. Now, so this truss brace tube system or the brace tube system was used here in the John Hancock Center. It is similar to tube in tube, but few and farther spaced exterior columns. Remember what I told you in that case? In that case I told you that the columns are very close spaced together, and there are these spandrel beams that are joining them. It is a very dense series of structural members, beams and columns, and window space becomes smaller, and that it works like a tube. But in this case they have increased the space between the columns. There are fewer and farther spaced exterior columns to provide for more window space. But when that happens, they have provided these steel bracings. These steel bracings have been provided like this along the exterior walls to compensate for the fewer columns by tying them together using the bracing. And thus this was done in the John Hancock Center. It was done using something called the chevron mechanism in the Citicorp Center. It was done in the Bank of China Tower, and we look at those examples also. But what we find here is an alternative to the frame tube is the brace tube. Variations of the truss of the brace tube, like in the case of the Bank of China, it is a triangular truss in composite steel in RCC, and in the case of the Citicorp Center in New York by Hughes Stubbins Associates in 1978, it does these inverted chevrons that you are able to see here in the sectioned part of the building. Now when we talk of the John Hancock Center, if you look at the structural expression, there is clarity of columns, clarity of diagonals, and the clarity of tie members, and this is the architectural expression of the building. That means the building structural members are now playing the role of giving the aesthetic form to the building. And this is something that we will talk about more in the coming lectures, where architects started using the filigree of structural members or structural members as the aesthetic of their building, for which this building has been remains known for decades after its completion. It's still famous because of this innovative structural feature on its facade. Now, without the bracing, without the wind and gravity loads, without bracing, the wind and gravity loads are largely handled separately, but with diagonal bracing, more even redistribution of loads takes place. That is, the brace tube handles loads in a more integrated manner, and the tube actually becomes like a stiff box, So you see it here. For example, there are these two load points of 70 kip each right at the top of the John Hancock Center, and this axial loading is there. As the load travels down, it gets dispersed into 7 different load carrying columns or load carrying routes, and the load gets divided. 140 kip of load gets divided into 20 kip each carried by 7 streams, and this becomes 20 by 7 columns, and again a total of 140 kips. So it begins with 270 kip point loads applied symmetrically at the top of the building. As it ascends, the cross bracing helps to spread the load between the columns until there are 7 columns carry this load, each of 20 kip and no more. So that is how load transfer takes place by the use of bracing in the brace tube construction. Now the triangular truss is what you are able to see in this night view of the Bank of China. It is in composite steel and RCC, and the steel truss framework is filled with flush steel glass structure done very aesthetically smoothly. The facade and skeleton are a flushed surface, completely flushed. So what is the building system? The floor plans vary with height, but the building core, the stairs, the ducts, the lift, they rise through the center and link all the building floors. So even though the shape of the floors at different levels is different, the core continues to remain static and provide that connection through and through the building. The weight of the structural steel is much lower than other tall buildings that were built in the Far East during this time. This was partly achieved by the efficiency of the overall structural form. How they did that was by the construction of megastructure joints. Megastructure is a composite steel and concrete construction for joints and members. Conceptually, it was done like this. There is a stack of 5 12-story buildings like this, each supported by the megastructure, and in each of them it has got floor designs like this, in which there is this one center mega column here, having 4 mega columns, one at each corner, and the 5th central mega column which is required at higher levels, So when we have the central mega column, if you look at it here in this picture, this is the central mega column coming from the top. It stops at level 25 and then it disperses its load by these two diagonals towards the side, and then the load is transferred downward by corner mega column. So this is carrying the load from the top down all the way till level 25. The load gets transferred here to outer mega columns and then to the ground. So thus this whole pyramidal form or structure helps to transfer the overall load of the building to the ground using the system of mega columns. In the John Hancock Center, which was a brace tube structure, the load transfer was done by having those 2 big columns at the top, and through bracing the load was finally transferred to 7 columns and they brought down the load to the ground. In the case of the Bank of China, the mega column transfers it diagonally to external mega columns and they bring it down to the ground. Now we come to tube in tube, a tube within a tube. There is an outer frame tube of dense columns and deep beams as in the case of the original frame tube. and it is combined with an inner core tube. So here you see outwardly you find this dense beam and column structure on the outside, and then there is an inner core which is actually not placed right in the center but on one side, containing the elevators, the stairs and the mechanical systems. The inner and outer tubes, they work together to resist gravity and lateral or wind loads. But most lateral load are borne by the outer tube because it has greater structural depth. But why tube in tube? See, the large open column is free of, there is the open column free space in the office is provided. As you can see, there is no column in between. There is excellent lateral stiffness without the external bracing. Efficiently distributes gravity and wind loads between core and perimeter frame. Because of again the core and the perimeter frame being connected to each other, there is a load transfer happening between the both of them also, and they work in tandem with each other to maintain the stability of the structure and face both the gravity and the lateral loads. Then another tower that came up in the tube in tube form is the Petronas Tower in Kuala Lumpur in 1998. Twin towers of glass, steel and concrete, one of the world's tallest buildings and symbolic gateway to Malaysia, required a proposal that was distinctly for Malaysia, and the architect Cesar Pelli said, this is not necessarily Malaysian, but it is a structure which will forever be identified with the city. And how true he proved to be. Today this picture, wherever you see it, you can connect it directly to Kuala Lumpur. It is a conscious departure from modern architecture in that modern architecture tends to avoid symmetry, but this building, it reinforces symmetry in the building. The towers are identical in form and height and are also connected by a sky bridge. The verticality is emphasized by receding floors and tilting walls which are tapering towards the pinnacle. Now there are these rotating squares that you see here, these rotating squares resulting in 8-pointed star, and geometrical complexities then generate plan form based on Islamic geometric traditions. As it keeps on getting more and more complex, we get the Islamic geometric tradition. While views are welcome, tropical sun is not welcome, therefore horizontal ribbon windows are relatively narrower than they would be to keep out the tropical sun's glare. There are projected sunshades and multifaceted walls which create a tropical skyscraper. So the skyscraper has been designed keeping in mind the climate responsive nature of the skyscraper vis-a-vis the city of Kuala Lumpur. Now it has a sky bridge and its tube in tube. The structural system of each tower, there is in each tower there is a central core of 25 meter by 25 meter. There is then an outer ring widely spaced, 16 cylindrical super columns are placed. In this outer ring, widely spaced 16 cylindrical columns or super columns are placed. The 16 super columns are made in high strength RCC. They are linked by this ring to build a moment frame outer tube, and what you find here finally is that there is an outer tube and there is an inner tube. It is a combination of outer and inner tube, and it is a good example of tube in tube system or a pair of soft tubes. So we will end here. This is how different structural systems have evolved in the 20th and the 21st century. It began with the simple moment frame structure, but as buildings began to grow taller, we required something different. So they started coming with the tube frame system, in which bracing was required, in which tube in tube construction was required, and there are some more that we will see in the next presentation, where I will take up some more examples to explain the frame tube construction in its various forms. And so we will end here for today. Thank you.